Okay, hello, welcome back to CS 700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. So last time we have talked about encodings over basic spaces. Our basic spaces are Cantor space of infinite binary sequences and bare space of infinite integer sequences. And these spaces can be encoded one over the other, but actually we don't need such encoding because our model of computation, while plus programs actually already are designed to operate in these spaces. We need to talk about encodings only when we are dealing with other spaces, and we have learned how to formalize such encodings, namely the technical term is a representation. A representation is a surjective partial mapping from one of the base spaces onto the set X, which we're interested in studying computability here. So a name of an element in this set is an infinite binary sequence or infinite integer sequence, which is assigned to that element by the representation. And we have thus reviewed the notions of computability for single real numbers that we studied much earlier, now in terms of representations, namely the three notions that we know are equivalent, gave rise to three representations. The binary computability corresponds to binary representation. Uh, Approximation by rational numbers by fraction corresponds to the rational representation, and approximations by dyadic rationals corresponds to the dyadic representation. So that this is a generalization of what we've already learned before, computability over real numbers, real sequences, and so on. And our goal is now to generalize this to very generic spaces so that we can, when we want to study computability, let's say over Hilbert space or over um, over Hilbert space or Banach space, and we can immediately do so using our generic representation for Hilbert space or for Banach space. And towards this end, we need to identify which representations are actually reasonable ones. We want to classify and characterize different representations of the same space. So, and first we've defined what it means to compute a function or a multifunction between spaces that are already equipped with a representation. And there it came in handy that we have already defined what a multifunction is. We defined composition of multifunction, and thus all the nice computability properties for functions between represented spaces would immediately extend to properties of computable multifunctions between represented spaces. For example, closure under composition. You remember the special kind of composition, and closure under restriction. Remember, we have had this standard and variant notion of restriction for multifunction, and we've seen um, it follows immediately that every computable function is closed under restriction. That's because of our definition that we don't require any special behavior of the computation on arguments that are outside of the domain. But similarly, it turns out that also computable multifunctions are also closed under this other kind of restriction where we restrict, namely the codomain, the values of the function. And then in order to study and to compare different representations of the same space, we have introduced the notion of a continuous reduction. Now you know reduction, computable reduction in CS 422 computability theory, the first part, and of course polynomial time reduction, the core of the definition of the famous complexity class NP complete. Now here we have also a notion of reduction, but the objects which we reduce here are very different from the ones that we study in discrete computability and complexity theory. Namely, the discrete realm we consider decision problems. We already seen that decision problems in the setting of real numbers are trivial because any decision problem is a discontinuous problem and therefore uncomputable trivially. So when we want to study reduction for continuous problems, we actually do need new notions that still should, of course, satisfy the similar nice properties, in particular, a property like transitivity. And here we saw such a definition, namely a continuous reduction from one representation psi prime to another representation psi means a continuous realizer of the identity mapping from the space X to the space X, which makes sense because we're comparing two representations of the same space X. And now recall what it means to be a realizer of such a mapping in general. It means to convert psi prime names to psi names, in this case of the same element. So here is this spelled out. This reduction means a continuous, right? We're talking about continuous reduction, a continuous mapping from the domain of the first representation psi prime, which is one of our basic spaces, kind of space or Baire space, to the domain of the second representation psi, such that f, that's the intuition how I memorize this, f translates psi prime names to psi names. Namely, if we apply the right hand side of this composition to a psi prime name of something, then f should translate that to something which psi then maps to a name of the same element. So that's the same thing. And here we use again this notion of a restriction, or rather right hand side the opposite, an extension, because we don't prohibit f to do what f should do on arguments that are outside of the domain, can be undefined or produce anything. So, and then using this notion of reduction, we have actually now returned and to our initial question, and now we've compared the representations of single real numbers. We already know that their computability, which is a non-uniform property, is equivalent. A real number is binary computable if and only if it is rationally computable, if and only if it is dyadically computable. But is it also possible to convert algorithms for binary computation to an algorithm performing a rational computation of the same name, of the same real number, and vice versa? And how about conversion to and from dyadic algorithms that compute dyadic encodings of the same real number? And we've seen that actually there some of the equivalences break down when we look at them in the uniform setting. So we can convert easily to the row representation, the rational representation. We can convert everything to the delta, to the dyadic representation. We can convert between them, but we cannot convert to the binary representation, neither the rational nor the dyadic representation. We can convert from the binary representation, but not to, at least not continuously. And that's an important point here. You already know that continuity is an important part and aspect and perspective on um, real computation, and this merges here and will reappear frequently also in the sequel. So this means that these representations are not uniformly equivalent. That has been reflected in our proof. And when we prove that if a real number is rationally or dyadic computable, then it is also binary computable. Our proof would consider different cases. In which case to apply uh, was uh, um, was our choice as scientists in the proof, but the choice can, that's gist of this non-reducibly, this choice cannot be made algorithmically. So which case currently applies among the several cases is not accessible to an algorithm. Algorithm cannot kind of hybridize the different uh, cases into one algorithm. They are indeed separate algorithms that compute the binary expansion of a real number, uh, depending on whether the real number is a dyadic rational, in which case we hard code it, or whether the real number is not a dyadic rational, in which case it indeed is possible to convert back and forth algorithmically. So that was our notion of continuous reduction and its application here for the toy example, if you like, of representation for single real numbers. But of course, this notion of reduction is designed as a powerful tool to compare reductions and to identify reasonable from unreasonable representations for more general and more abstract spaces, but we'll of course use the real spaces that we've already investigated before as a guideline for our tools and criteria. So next, another way of comparing representations is by comparing their domains. Um, so in particularly, what topological properties do the domains have? And here um, it depends, of course, on the domains and the codomains of the representation. So Cantor space is a complete metric space. Bare space is a complete metric space. Cantor space is compact, but bare space, as you recall, is not compact. And here we consider representations of the real unit interval, which is compact, whereas we can extend that to representations as an entire real line, but the real line is not compact. It's also a complete metric space, but not compact. So, and this differences about compactness or non-compactness of the domain and the codomain will now become apparent again, because recall that our representations have domains which are a subset of Cantor space and bare space. They are partial surjective mappings. So let's look at these domains again. It turns out that the domain of the rational representation is not compact. It is closed. Yeah, it's the pre-image of the closed unit interval under continuous representation, right? All three representations are continuous. So if we take the pre-image then of a closed set, then we arrive at the closed subset of bare space, but not as at a compact set. Pre-image of a compact set under a continuous function is not compact. Pre-image. Image of a compact set under continuous function is compact, but pre-image in general is not. And this is exactly what happens here. And to illustrate that, observe that we can change the name of just a single real number. Let's fix any real number, let's say 1, and create many names of that real number by artificially multiplying both numerator and denominator here with some arbitrary natural number, that doesn't affect the approximation at all, but it does affect the name, namely the sequence an of integers, namely the element in bare space. It becomes unbounded, an unbounded sequence of bare space elements, and therefore this cannot be compact. Notice that a similar blowing up of names is infeasible for dyadic representation, because here we have fixed the denominator to be 2 to the n, and therefore also fixed the numerator to be between 0 and 2 to the n, right? And that's a large, exponentially large, but a finite set. And according to our criterion for compact subsets of bare space, remember Koenig's lemma, compact subset of bare space means finitely branching and closed. And this means it is finitely branching. So if we have the element an, the nth entry in a sequence, and we consider the n plus first one, then there are only finitely many successors, so that the subset of bare space of all names of the unit interval is indeed finitely branching. The next successor can have only integers from 0 to 2 to the minus n plus 1 because it's a successor. And this is the idea of the proof that the domain of the dyadic representation is indeed a compact subset of bare space, the set of all binary sequences that are A, have values between 0 and 2 to the minus n, the nth element. That's the finitely branching part. And that satisfy this Cauchy condition, namely that the distance between the nth and mth sequence element, a n divided by 2 to the n, must differ from a m divided by 2 to the m by at most 2 to the minus n plus 2 to the minus m. That's a Cauchy condition. All integer sequences that satisfy these two requirements, integer values between 0 and 2 to the n, first condition, and secondly, this Cauchy condition, these are precisely the integer sequences that are names of real numbers between 0 and 1, and this is easily seen to be a compact subset of bare space. And similarly, the domain of the binary representation can also be seen to be compact. So these are kind of good properties for the binary and dyadic representation, but bad for the rational representation. Whereas in terms of reduction, it seems like the rational and the binary and the dyadic representation have good properties, but the binary representation does not. And only one representation shares both good properties, reducibility, and having a compact domain, and that's the dyadic representation. And particularly when we're interested in complexity investigations later, much later, then we're going to use, for this reason, we're going to use the dyadic representation. So, right. So to summarize, the dyadic representation is nice. It has a compact domain and it has full reducibility. The rational representation has also full reducibility. It is reducible back and forth from and to the dyadic representation, but its domain is not compact. The binary representation does have a compact domain, but it suffers from lack of reducibility. And now we're ready to formulate an important criterion for representation to be computability theoretically reasonable, sensible. And that condition is actually pretty subtle, and it's a important achievement to have identified this condition. Just to remind you, it also took a considerable time throughout centuries to find the right definition for continuity, right? So before Cauchy and Weierstrass, there was no definition of continuity, and actually people, mathematicians implicitly considered only continuous functions without really knowing their or realizing their blind spot, nor without a formal definition. And similarly, it took several attempts and revisions to arrive at what we nowadays use as definition for compactness. So here, definition is a crucial uh, um, achievement, and this definition is due to Kreitz-Weihrauch from 1985. They define a representation to be admissible if it satisfies two conditions. First condition, it must be continuous. That seems like a reasonable definition, remembering that every computable function must necessarily be continuous in the real case as well as in the case of the basic spaces. But here, of course, when we talk about representation, uh, that their codomain is neither real nor basic space in general, because their goal is to define computability on this space. But it seems like a good guideline to require continuity for the representation. Um, and the second condition is kind of a maximality property, namely that every other continuous representation of the same space admits a continuous reduction to this representation. So this representation is in a sense supposed to be maximal, right? With respect to this partial pre-order, right? So this is a partial order. Not any two representations are comparable in this sense. And also it's only pre-order if two representations can be reduced to one another. It doesn't necessarily mean that they are actually equal, right? Of course, we're going to define them to be equivalent. We're going to consider equivalence classes, and then this is actually going to be an actual partial order, not just a pre-partial order. Right. And again, let me remind you of a similar definition of a decision problem to be NP complete. A decision problem to be NP complete means two things. First, it must be inside the class of NP that corresponds to our first condition. And the second condition is a universal property. Every other problem in NP must admit a polynomial reduction to this problem. And that's a corresponding part or the item 2, namely here it's basically very similar. Every continuous representation must be reducible to our representation. So this seems like a categorical property of spaces with a partial pre-order. Consider the maximal elements of this space, here the space of representation, and this seems to be interesting objects, categorically speaking. Okay, so let's now have a look again at our three example representations for single real numbers with respect to their admissibility as a third criterion. And here turns out that the representation beta is not admissible, which is another disadvantage, whereas the other two, the representation rho of rational representation and the dyadic representation delta, these two are admissible. So that's another advantage for the latter two. Now, why is the representation beta not admissible? Well, let's check the first condition. Is it continuous? Yes, it is continuous. That's easy to see. So how about the second condition? Every continuous representation can be reduced to the binary representation. Now, unfortunately, this is exactly what fails here. Namely, we already know that the rational representation is not reducible to the binary representation, and the rational representation is also continuous. All three representations are easily seen to be continuous, so the binary representation lacks this universality, this maximality property, and therefore is not admissible. Whereas the representation rho and delta, they are both admissible, they're both continuous, and they both satisfy this maximality requirement that any other representation can be reduced to them. I'm not going to prove the latter, but I'm going to uh, prove something more general on the next slide, so please stay tuned. So that's important evidence for the representation rho of rational approximation and the dyadic representation delta to be actually the computability theoretically reasonable ones. And only when we proceed to complexity question, then also the rational representation rho drops out of the picture and only the dyadic dyadic representation remains for now. We're going to introduce another representation when we talk about complexity. Okay, so I've already announced that we're going to learn more about admissible representation, and in the most important question that every scientist should ask after such a definition, um, do admissible representations always exist? Right? I mean, we can define something, but if no such object exists for some spaces, then that's a void definition, the definition of the empty set. And as you recall, the famous Stephen Cook theorem says that there exists NP-complete problems in nowadays terminology. Otherwise, the definition of being NP-complete would have been could have been pretty boring a definition, right? But we know by Cook's theorem that there exists an NP-complete problem, namely the Boolean satisfiability problem. And Richard Karp then identified many more problems as NP-complete. Similarly, what we're going to learn on the next slide is that a large class of spaces actually have admissible representation. But let us wrap up this slide with the important, sometimes so-called main theorem, which was identified and proven by Kreitz and Weihrauch, also in 1985, when they found this notion of admissibility. And the theorem says, if we have admissible representations of the domain X and the codomain Y of a function we're considering f, then this function is continuous if and only if it has a continuous realizer. And remember that a realizer is a mapping on our basic spaces where we don't need to define coding or computability because it's already defined. And also recall that we know that any computable realizer must be continuous, and this can be seen as a counterpart, as a characterization of all functions which have continuous realizers. Namely, this is precisely the class of continuous function, which is a pretty neat characterization if you think about it. Put differently, it means that our encodings, admissible encodings, are those that translate topological property from functions to their via their representations to the basic spaces and back and forth translation, not just of names, but also of topological property, namely of continuity. Yeah, this theorem actually is not hard to prove once you have the notion of admissibility. From my perspective, I think having identified the concept of admissibility, that's the main contribution. Similarly to having found the notion of polynomial time reduction, Stephen Cook is the main contribution. And then, of course, a proof that there exist NP-complete problems. And similarly, now we're looking at the proof that many spaces have an admissible representation, so that this is not a trivial notion, a trivial definition. Okay, so which class of spaces are we going to look at? We're going to look at the topological spaces which satisfy the T0 separation axiom and have a countable subbasis. So two conditions are kind of hidden here in this definition. First condition is the T0 separation axiom. So let me remind you of that. It means that to every 2 points, there exists an open set which contains the first point but does not contain the second point. And vice versa, of course, by changing the roles of the 2 points. So this is kind of the weakest, arguably, of the separation axioms that one usually imposes on topological spaces. There's this hierarchy like T0, T1, T1.5 sometimes, T2, T3. There's also sometimes something called T3.5, and then T4 separation axiom before we proceed further to topology, to metric spaces which satisfy all the separation axioms. Right, so that's the first condition, very weak separation condition. And the second condition is kind of to be separable. In metric spaces, we call this separable, namely having a countable basis, or more precisely, a countable subbasis. And I leave it to you to check that if we have such a T0 space and a subbasis, then also the subbasis separates elements in the sense that to every point there exists an element in the subbase which contains the point and does not contain the other point for every 2 fixed points. So that the separation axiom can be also stated in terms of a subbasis. Now, yeah, what is a subbasis again? So remember what the topology of a space is: a family of subsets which we call open, right? And which are closed under arbitrary unions and under finite intersection and contain the empty set and the entire space. And the basis of a topology is a subset of the topology, again, a set of open subsets, but not necessarily all of them, such that any other open set can be expressed as a union over the sets in the basis. So the basis kind of generates the topology by taking arbitrary unions. And the subbasis is again a set of open subsets, but which is even smaller. Namely, subbasis generates a basis rather than, and the basis then generates the topology, where the subbase generating a basis means taking finite intersections. So a basis of a topological space has to be closed under finite intersection, but taking arbitrary unions then generates the topology. And the subbasis, we have to or may first need to take the closure under finite intersections, and then proceed to arbitrary unions to generate the topology. So that's a subbasis. And yeah, if you're not familiar with subbases, just think as a basis. And if you're not familiar with spaces, just think as the collection of open balls with dyadic centers and dyadic radii, open balls, if you prefer to think in the particular setting of metric spaces. Okay, and if we have such a space, this is sometimes also called a Kolmogorov space, then we can define a representation generically without even looking at other properties from the space rather than its topology. And this we'll call the standard representation with respect to this subbase. So if we take a different subbase that generates the same topology, then we might end up with a different representation, which may or may not be, well, actually it turns out that it will also be equivalent, reducible back and forth, because we're going to prove that any standard representation first exists and secondly is admissible. So that here we prove basically that every Kolmogorov space with a countable subbase um, has an admissible representation, which you can see as a counterpart to Cook's theorem that says there exist NP-complete problems. Okay, so here's the definition of the representation. Let me call that representation Xi. And remember, representation assigns to some sequences of integers an element in the space. And this sequence of integers, element of Baire space, is called the name of that element here. So we define here what the Xi name of an element is. It is a list of all natural numbers in any order, right? An infinite sequence of natural numbers. Recall this is an element of Baire space. Not all Baire space, right? Because we only fix integer sequences, natural number sequences. And here a name must list in any order all indices of the subbase that contain the element X. This can also be regarded as listing all positive properties. Tell me in which elements of the subbase the given element lies. Okay, and that should tell us everything we need or we can know for computing with this element, computing maybe on this sequence of natural numbers. And indeed, the theorem says this so-called standard representation is admissible. And the subtle point hidden behind that theorem is that it actually is a representation. So why is it a representation? Well, because the important question is if we have two identical names, if we have a Xi name of X and a Xi name of a different element X prime, does it follow that X is equal to X prime? This is necessary for representation, right? Because remember, a representation is a surjective partial mapping. In particular, it must be a function. We cannot have here, at least in this lecture, a multi-valued representation. It must be functional. So when we put the same name into the representation mapping, then it should be the name of the same element, or put differently, two different names, elements must have only different names. And this is exactly what is asserted by this T0 Kolmogorov property together with the subbase being countable, right? So the countable subbase gives rise to this being a list, right? We can only list countably many elements. We cannot list uncountable number of elements. That's an oxymoron. And this list should uniquely identify which element point in X we're talking about. The representation must be functional, not a multifunction. Two different names, no, the same name, twice the same name must refer to the same element. And this is exactly what happens here. Then if we have a different element X prime, then by the separation property, there exists an element in the subbase. There exists some ON, which contains the first point, but does not contain the other one, right? That's the very definition of the Kolmogorov T0 property for the topology. But that extends and applies also and holds also for a basis, for any basis of a T0 space. And furthermore, it extends to the subbase we're considering. So whenever x and x prime are distinct elements in the space, then there exists an subbase element. There exists an integer n which contains the first, but that's not contain the other one, and that means yeah, that the two lists must be distinct. One list contains on, and the other list cannot contain, must not contain. So now we've checked that this is indeed a representation that is well defined as a mapping from, in this case, bare space, partial mapping from bare space to onto our space X. And it is surjective, yeah, obviously, because we can take any element X in the space X and just take the list here in any order. Let me point out a subtlety that we reserve in this list the entry 0 for padding purposes, right? So the subbase we consider here uses indices that start with 1, only positive natural numbers, and 0 in the name, by definition of the standard representation, is kind of a blank pause symbol, like yeah, a filler, and that will become relevant in a minute when we know proof that there is a representation is not just well defined, but it is actually admissible. Okay, and for admissibility, let us recall what are the two properties of an admissible representation. Admissible, first property is that it must be continuous, right? That was the first property. So let's check, why is this mapping continuous? And here's a proof. How are we going to prove continuity? We're going to prove that the pre-image of a closed set, of an open set, sorry, that the pre-image of an open set is open. Okay, so remember Xi is our mapping from our base space, counter space, onto the space X. And in the space X, we have this subbase. So in particular, we have an initial supply of open sets, named the sets in the subbase. And being continuous means the preimage of an open set must be open, in particular the preimage of the subbase element. But actually, the preimage of every open set must be open. But we already know that the subbase generates the open set by finite intersection, here for instance a binary intersection, and by union. And of course, preimages are closed under intersection and union. So it suffices if we consider just single subbase elements, then the preimage of that. But for illustration, pedagogical purposes, I have here included also binary intersection, and leave it to you to generalize or to convince yourself that this is no restriction at all. So what is the preimage of this intersection of these two open subsets of the space X? Right, so what is the set of all names of elements X that belong to this or and to this? Right, so to belong to this means that in the list, let's call this list U. U is a element of bare space. In this element, in this list U, somewhere the index n must occur, right? This means that n occurs in this list by the definition of the standard representation. And let's say that the kth entry in that list is n. For some k, there's no requirement where in the list this entry n must occur, it just must occur. So we're taking here the union over all possible positions k in this list where n occurs. And similar, since in this illustrative example we consider the intersection with the other subbase element m, somewhere the entry m must occur in the list U. let's say at some position L, and we don't know which, so this is the union over all of them. So we have thus expressed the preimage of this intersection of two subbase elements as a union, countable union of this set. And now recall what is the topology of Baire space, what is the basis of the topology of Baire space, basis of the topology of Baire space subbase. I think a subbase is the set of all sequences where one entry is fixed. So if we consider all sequences where the kth entry is fixed to n, then by the very definition of the topology, this is an open set in Baire space. And if we fix two elements, that's also open because the open sets are closed under finite intersection. So that this is indeed an open set. And here we have a union over open sets, which is open in Baire space by the very definition. So we've just proven that the preimage of subbase open subbase elements is of the space X is an open subset of the Baire space, and therefore this is indeed a continuous function. And I'd like to point out again that here we've used one of the many equivalent definitions for mapping to be continuous, but a rather modern definition. This is not the Cauchy or Weierstrass epsilon delta definition for metric spaces. This is the general definition of continuity for topological spaces. Okay, so now we've established the first requirement for representation to be admissible, corresponding to the proof that in NP completeness that the problem is in NP. Now we need to prove kind of the harder part, the reduction. Now here the reduction from any other continuous representation to the representation Xi, the standard representation. So let's consider an arbitrary continuous mapping from Baire space to X, and actually in nice property, important property of the standard representation is that this reduction, continuous reduction, holds not only for the representations, other continuous representations, but for any other continuous function. It doesn't have to be surjective, but this is a property of the standard representation. So we're going to prove something a little bit more than that the standard representation is admissible by asserting continuous reduction from arbitrary continuous functions Xi prime, not just from representation. Okay, and before we construct this reduction, remember here's the definition of this reduction. Continuous translation from Xi prime names to Xi names. And before constructing this, let us recall one of the standard bijections between pairs of natural numbers and natural numbers, which is sometimes called Hilbert Hotel. So here's such a typical example. The interesting thing is that it is actually bijective, although the domain are pairs of natural numbers and the codomain are natural numbers. Still, both have the same cardinality, both are countably infinite, both can be put into a bijection, and Hilbert's Hotel has a way of doing so explicitly. Now we use this to define our actual reduction or conversion from Xi prime names to Xi names. And this is the definition, and you see here how it involves this Hilbert Hotel. Namely, so the argument to our reduction is an element of Baire space, an infinite sequence of integers in the domain of Xi, right? So we need to convert, we're given a Xi name and need to output, we're given a Xi prime name and we need to output a Xi name of the same element. And so here's the definition. So take the image of Xi prime under this initial segment, right? So the argument to our translation function is an infinite integer sequence, an element of Baire space. and we consider only the first few elements of that sequence, and then extend that with arbitrarily to an infinite sequence, right? So this here means append, concatenate, and this means arbitrary infinite sequence of integers. So, and then we take the image of that set. This is a subset of Baire space, a set of infinite integer sequence. And we take the image of that under our arbitrary but fixed representation psi prime, which we only know to be continuous. And we check. So when I say we, I mean in our proof, in our definition, not algorithmically, we check whether this is a subset of the mth subbase element that we're considering. Okay. And now here you see two parameters, J and M, and these are actually these parameters together define which element of the output of the translation we're looking at. Remember that the translation reduction receives an element of Baire space as argument, an infinite integer sequence, and must output an, something in the domain of psi as output, an infinite sequence of integers again. And in this infinite, we define this infinite output sequence term-wise, and then we will here define the m comma j term, where m comma j are combined into one index because it's not a double sequence, but a regular sequence that we need to output. So we define what is this element with this single real integer number as the index in the value of this. And we define this to be m. Well, that's the index of the subbase element, which we've just determined or concluded to contain the image under this initial, any extension of this initial segment, if it does. Otherwise, we define the value to be just the integer 0. And remember, 0 is what we use here for padding purposes. This basically means the same as I don't know yet. So if this property does not hold, we never say it does not hold. We only say we don't know yet. Okay, so that's the definition of the reduction. And now we need to verify that this reduction is continuous and actually a reduction satisfies this property. So why is it continuous? To see that it is continuous, let us try what happens if we modify the argument v, the infinite integer sequence v. If we modify that beyond the jth element of that sequence. Okay, so if we modify the j plus first, j plus second, or any other, so we fix the first up to the jth element and only apply changes to the later elements. And in Cantor space, Baire space topology, that means we apply perturbation of magnitude less than 2 to the minus j. Now what happens with the value? Well, the value remains the same for all positions with index j less than the one we're considering. So that means our perturbation of the argument can only affect values of our translation, the value gain being Baire space infinite sequence of integers beyond the m comma j's element, and proves that the value of m comma j paired in Hilbert's hotel is greater than j. Yeah, you can see that here. So that perturbing v beyond the jth element will perturb f of v also only beyond the jth element, and that's the very definition of being continuous. And that's the first thing we need to check here, right? A continuous translation, and it must be a translation. So we also need to check that this f translates psi prime names v to psi names u of the same element. And now why is that? So what do we need to output? According to our definition of Xi, we need to output a list of all indices M here that contain the element X under consideration. So let us consider Xi prime of V, right? Xi prime of V is some element in the space X, V being a name of this Xi prime name. And if this element X belongs to OM, the open subbase set, then M must somewhere occur at least once in any order with repetition must occur in the output list, if and only if the element X belongs to OM. Now, if it belongs to OM, then since Xi prime is continuous, right? That's the hypothesis. Xi prime is continuous, therefore, for finite, sufficiently long but finite initial segments, all extension will land in this open set. That's an equivalent definition of being continuous, right? Function is continuous if for every um, uh, neighborhood on the codomain, there exists a neighborhood in the domain which is mapped inside this neighborhood. So for sufficiently large J, this is such a neighborhood. This is the definition, the basis of Baire space. So for sufficiently large J, this will then hold and thus result in the output of M into that list. So, and conversely, if the point X, whose Xi prime name V were given, does not belong to OM, then this will never happen, right? Okay. So that this is indeed a translation from Xi prime names to Xi names, which is continuous, and that's the second definition of being admissible. And this first definition, we've already verified that this is continuous, and thus this concludes the proof that the standard representation is indeed admissible, and therefore every Kolmogorov, topological Kolmogorov space with countable subbases has an admissible representation, namely the standard representation. Okay, let's now play around a little bit with representations. Namely, if we have representations for spaces, how about the Cartesian product of the space and the Cartesian product of the representation? Yes, so indeed, it is true. If we have representation Xi of the space X and a representation epsilon of the space Y, then this gives rise canonically to representation Cartesian, which we call Cartesian product representation of the Cartesian product of the two spaces. And soon we will also see that if the original representations were already admissible, then also the product representation will be admissible again. So, and our definition of this product representation again makes use of the pairing function, but now not as a pairing function pairing pairs of natural numbers as in Hilbert's hotel, but here pairing two elements of Cantor space or Baire space. So let's say U and V are both infinite sequence of bits or infinite sequence of integers. Then by alternating them, we arrive again at an infinite sequence of bits or an infinite sequence of integers from which the original sequences, of course, can be recovered as elements with even or with odd indices, respectively. So that this is again a pairing function, but now a pairing function that combines pairs of elements from Cantor or Baire space into one element of Baire or Cantor space, whereas the original Hilbert hotel combines pairs of natural numbers into one natural numbers. But this is also nice to be called a pairing function because it bijectively maps elements from pairs of the same space to one single space. And this is what we use here. So given kind of two two names combined into one single one, then recover the first and recover the second as those with even or with odd index, and translate them, recover the original element there, for which this is the name, in this way, and then consider the pair of the two so that it's easy to see that this is indeed a representation, surjective partial map. Okay, and since we're at it, let's continue the same and consider countable pairing. So here we're given a family, a sequence of elements from their or counter space. So every U here, every single is itself a sequence of, let's say, integers, and we combine them into one large sequence of integers in this way by using now the Hilbert Hotel pairing function here as index. So naturally this would give rise to a double sequence, right? One index for which U we're considering and another index that tells which entry in that U we want to consider. Like here, we want to consider the nth entry in the J's sequence. And we combine both indices into one to make this back into a single sequence, into a single element of counter space. So this is countable pairing. And we use that to construct a representation of the countable finite or countable Cartesian product of the original spaces. So let's say here J, we have a set, finite or infinite set of natural numbers as indices. And for each small j and capital J, we have a space xj, and this is already equipped with the representation xi j. Then consider the countable product, finite or countable product of these spaces with j ranging over capital J. This is naturally equipped with an induced representation defined in just this very way using this countable pairing function. Okay, that's easy. And now we're in business, then we know we can generally consider and reconsider our computability of sequences of real numbers, right? So sequence of real numbers is basically just a countable product of the set of real numbers. And we have already agreed on a representation for the set of real numbers. So taking the countable product of that gives rise to a natural representation for the set of sequences of real numbers, and we can now reconsider all our computability studies under this generalized and uniform setting. Representation for the set of sequences of real numbers, arbitrary sequences. Similarly, when considering only countable, finite Cartesian products, we arrive at a natural representation for the set of finite dimensional vectors of real numbers, arbitrary but finite dimension uh, uh, real numbers. Right. So now we can reconsider computability of tuples, finite tuples of real numbers, and that includes computability over complex numbers and finite tuples of complex numbers simply by pairing two real numbers as a real part and imaginary part of the real number, a complex number under consideration. Also polynomials. Polynomial can be identified with their finitely many coefficients, right? Every polynomial has an arbitrary but finite degree and therefore an arbitrary but finite number of coefficients, which we can put into a vector of real numbers so that we arrive also at a canonical representation for the space of real polynomials. And now playing the same game again, taking countable Cartesian product of the space of the representation for real polynomials, we arrive at a representation for the space of sequences of polynomials. So this is just, playing around with the Cartesian closed constructions. So we have a representation for the space of sequence of polynomials. And why am I doing all this apart from enjoying this Platonic construction, categorical construction, because remember, we want to actually study computability of real numbers, of real functions, and we want to devise representations for the space of real functions, and it will become handy on the very next slide. But before that, let me state what I've already announced. Our categorical construction not only translates representations into new representations, but actually translates admissible representations to admissible representation. So if the original representations are admissible for x and y, then their binary Cartesian product representation is again an admissible representation for the Cartesian product space, and similarly for the countable case. So that's a strong indication that this construction is indeed natural and well behaved. But I've already announced our goal, then is for the rest for today's lecture is to devise representations for spaces of functions and spaces of sets. More precisely, we've studied computability for continuous function and computability for compact sets. So now we want to generalize that and put these investigations that we've already performed, rephrase them in terms of representations. But we already have a representation for a sequence of polynomials. And as you recall, one of the notions of computing functionals or operators was to operate on sequence of polynomial approximations. It was called the Weierstrass notion of computability, right? And so that we indeed have obtained here a natural representation for the space of continuous functions on some compact set, namely a name of a continuous function on this set is a sequence of polynomials with dyadic coefficients that approximate that continuous function up to r2 to the minus n, and this sequence of polynomials in turn is encoded in this very way here. Well, I understand that it takes some time to recover all this. I mean, every step here is a categorical construction to recover what that actually means, but you're computer scientists, you're used to this abstraction. You have already forgotten how a real number actually is constructed. You work with real numbers without needing to know how they're defined. You work with computers and don't need to know how transistors work as semiconductor um, uh, solid state matter, quantum matter theory. So similarly, yeah, the baseline is we've arrived at this representation for the space of continuous functions on an arbitrary but fixed, that's important, a fixed subset of Euclidean space as domain. So if we want to vary the domain, then this construction does not apply anymore. It's all continuous functions that are total on the same compact Euclidean domain. And remember that we also talked about computability of sets. And one way to study and investigate computability of sets was by means of this fuzzy distance function, right? So the fuzzy distance function, no, we considered two versions, the continuous distance function and the fuzzy distance function. What you see here is the continuous distance function. So this is a definition of the continuous distance function of a closed subset A of the space X, where X now is supposed to be a metric space. And since this is a continuous function, we already have a representation for this. This is a special kind of continuous function. And we have a representation for general class of continuous functions. So by kind of restricting this representation, which I call delta blank, honor Akitoshi Kawamura's PhD thesis. By restricting this representation, it's a codomain actually. We arrive at a representation for the space of compact subsets of X, right? So again, it's tedious to recover what that actually means throughout all this categorical construction, but that baseline is this is a nice and it's a admissible representation with respect to the Hausdorff topology on the space of all non-empty compact subsets of X. But we have also considered other notions of computability for continuous functions and continuous sets, and this is going to be the last slide of today's session. Namely, remember an equivalent but different definitions for computing a real function was not by computing sequence of Weierstrass approximating polynomials, but by combining two conditions. The first, the sequence of values of this function on a dense sequence dense in its domain, let's say all dyadic rationals that belong to this compact subset. This is a countable set, right? By putting this set into lexicographical order, we can consider this as a sequence, a real valued sequence, and that is supposed to be computable was one of the conditions, and the other was that the function has a computable modulus of continuity in the classical sense, in the discrete sense, as a mapping from integers to integers. Now, how does that translate into a representation? Here today, we're only going to translate the first part and ignore or postpone the second part because this is discrete. This is kind of boring. So this equivalent definition, non-uniform equivalent definition, also gives rise to a representation of continuous real functions. Namely, we already have a representation for all sequences of real numbers, and here's such a sequence of real number. So let's just define if we have a sequence of real numbers in this sense, and then encode that, this is going to be, we define this to be a name delta, the delta filled box of the continuous function. So that now we have another representation of the space of continuous function. And non-uniformly, we know we have proven that a continuous function is computable in this sense, if and only if it is computable in this sense. But how about the uniform setting? The uniform setting, can we computably convert back and forth, or do we need to consider distinct cases as we did when converting from the dyadic to the binary representation, which were also equivalent, but only non-uniformly we could not convert. Similarly, for compact subsets, instead of the continuous distance functions, we also consider the fuzzy distance functions, which I like to recall here for your convenience. And this also gives rise to a representation of the same space of compact subsets. We can restrict to dyadic arguments here, and this also gives rise to a sequence with the dyadic arguments and with natural numbers arguments and with the Boolean values plus minus 1, 0. So then this gives rise also to a representation of the same space. And again, we know non-uniformly if a compact subset is computable in this sense, then it is computable in this sense, and vice versa. But can we computably convert back and forth, or do we need to consider separate cases which a computer cannot distinguish? Only a mathematician in its proof can distinguish. And fortunately, it is true. The theorem says that the two representations for the space of continuous functions are reducible one to each other continuously, which will use this simple equivalence They are computably and they're continuously equivalent. And similarly for the two representations of compact subsets, they are also equivalent and they are all admissible. This one admissible with respect to the Hausdorff topology on the space of compact subsets, and this one admissible with respect to the uniform topology or the metric on the space of continuous function on this compact set. So to summarize, and this concludes our chapter 3 on computability theory of topological spaces. We have talked about computing on basic spaces, Cantor space and Baire space. We have seen how cost, algorithmic cost, corresponds to quantitative continuity, modulus of continuity, and how compactness is crucial to obtain runtime bounds that depend only on the output, but not on the usually infinitely many possible inputs. And we've discussed representations as a way of encoding spaces of cardinality of the continuum over all basic spaces and how to define computability over such spaces equipped with representations. We've revisited our real examples from this perspective and seen that indeed this is consistent. The generalization is consistent with the previous example. It generalizes the previous example. The previous examples serve us as guides. We've defined what it means to be a realizer of a function or multifunction between spaces that are equipped with such representations. We've formalized reduction as a way of comparing different representations, in particular classifying representations. And we learned the concept of an admissible representation as an important criterion for representation to be suitable, to be sensible. Namely, these are the representations where the famous main theorem holds, characterizing continuous functions between spaces equipped with admissible representations in terms of having continuous realizers correspond to continuous functions and vice versa. And we've seen that every topological T0 space, Kolmogorov space with a countable subbase has such an admissible representation, namely a standard representation. And then we've performed some categorical construction spaces for representation for sequence spaces, representations for spaces of continuous functions on compact Euclidean subsets, and representations for compact subsets equipped with the Hausdorff metric. So that wraps up our chapter 3 on computability on topological spaces. And next time we're going to start talking about computational complexity theory, and more precisely we're going to have a recap on the classical, the discrete theory of computational complexity, and particularly such compact concepts as and complexity classes as P, NP, sharp P, and P space will be reviewed next time. That's all for today. Thanks for your attention and see you next time.